Once upon a time, in the land of algorithms and data structures, there lived a legend known as the Kosaraju. Kosaraju was unfathomed by any problems involving directed graphs. Even the toughest, the ones that pose a problem for numerous mathematicians, was easily solved by Kosaraju. One day, the mathematicians struggled with a problem, that is to find a solution to know which road were the most important for maintaining the connectivity of network in a complex interconnected road. After months and months of struggling, they had no choice but to seek the legend, the Kosaraju algorithm. After looking at the problem, Kosaraju used two approaches to the problem, using depth first search to create a graph of the original network, then we applied depth first search on the reversed graph using the order of the finished vertices from the first search as the starting point. With these two approaches, it allowed Kosaraju to find the strongly connected components of the network. From that day on, Kosaraju algorithm reputation grew stronger and it had a new name, the King of Directed Graphs. So in this video, I will be talking about the overview, the complexity, and how Kosaraju works. So, created by the theorist and mathematician Sambasiva Rao Kosaraju, is the Kosaraju algorithm that is designed to find strongly connected components in a directed graph. It is very easy to implement, and the time complexity of Kosaraju allows the algorithm to be faster than other algorithms. Hence, it is widely used in analyzing relationships between group of data and simplifying data when the data is too large. Before I get into how Kosaraju works, I would like to discuss a few terminology. First is the directed graph. A directed graph is a graph where all edges have directions and are connected from one vertex to another. So for instance, in a social media platform, the edges can be denoted as relationships between the users, and the direction of the edge would represent the direction of the user's connection. The next is strongly connected components. It is a subgraph of a directed graph in which each vertex is reachable to other vertex through a directed path. And the last is depth first search, a graph traversal technique that explores a graph by traversing as far as possible along each branch before backtracking. So, looking at this directed graph, we can determine three strongly connected components, and that is 0, 1, 3, 2, 5, 4, 6, and 7. So how do we get these three strongly connected components? First, we look at a directed graph. So here we have 7 nodes, 0, 1, 2, 3, 4, 5, 6, 7. So let's take 0 as our first node. We would then look at the child node, which is 1. And then from 1, we will look at the child, which is 2. And then 2, we will look at 3. Since 2, 1, and 0 is visited, so we would push 3 into our stack. So we have 3. Note that when we are at the node 2, we have two options. One is to go to 3 and one is to go to 4. But in here, in this example, I chose 3. So once 3 is pushed into the stack, I would go to the next unvisited node, which is 4. So I will go to 4, and then 4 will go to 5, and then 5 points to 6, and then 6 points to 7. So 7 will be pushed to the stack. So this continues. So from 7, I will go back to 6, and then 6 will be pushed to the stack, and then 5, and then 4, and then 2, 1, and 0. So we've visited 0, 1, 2, 3, 4, 5, 6, 7, and with the order, we have pushed 3, we have pushed 7, and then 6, 5, 4, 2, 1, 0 into our stack. And this is done with depth first search. So once the first depth first search is done, we would then reverse the graph. So instead of 0 pointing to 1, now 1 points to 0. So how do we find these first strongly connected components? First, we would pop a number out of stack. And the first number that is popped out is 0. So from 0, we would look at the child. So we will go to 3, we will go to 2, and then we will go to 1, and it goes back to 0. So the visited node is 0, 1, 2, 3, and this will form our first strongly connected components. And since 1 and 2 is already visited, then we would just push this out. So the next node that we will look at is 4. So we popped 4, and then from 4, we look at the child, and then that is 6, and then from 6, it points to 5, and then 5 points back to 4. And there we go, we have our next strongly connected component, and that is 4, 5, and 6. So the visited one is 4, 5, 6, and this is our new strongly connected components. And the next one that we will pop from the stack is 7, since 5 and 6 is already visited. So when we pop 7, know that it points to 6, but however 6 is already visited, so 7 would be a strongly connected component by itself. So there we go, our 3 strongly connected components from the directed graph. Now, let's talk about the time complexity. So when the first depth search is initialized on the graph, it performs a linear search through all the vertices that are present in the graph. Since the outgoing edges of the vertex will also be explored and traversed once during the process, it yields the complexity of O bracket V plus E, where V is the number of vertices and E is the number of edges. And reversing the graph would be a time complexity of OV. So if we were to have 2 depth first search, that will allow us to have a time complexity of O, V plus E. So the worst case and the average case is the same, because for the worst case, it's basically having a number of vertices and edges at the max number. And for average case, it's just having a V number of vertices and E number of edges. And for the best case, you can see that it's just OV. So for the best case, this would happen when the directed graph is a tree, meaning that the Kosaraju algorithm would run the depth first search on each vertex once and explore the edges connected to it. So, since it's a tree, it would give us a time complexity of OV. And by creating this video, I have collected a lot of data from multiple references, and these are all the references that I have collected from, and this would sums up my video. Thank you for watching.